Okay, I think I got that going. Where did I put my marker? You see a purple marker in a random spot? It's in my book. All right. Let's hold my page open. Leave that, leave that. Okay. So last time we finished section 1.1, talking about finite automata, and in particularly what we were talking about were deterministic finite automata. What do we mean by deterministic finite automata? Let's draw one up really quick. So we have like a simple one that recognized contains an even number of zeros. So we'll do contains an even number of zeros real quick. I'll make this the accept state and start state. Call it Q1, Q2. So this is we have an even number of zeros, this is we don't. So if we see a 0, it's an odd number. If we see a 0, we're back to an even number. And then we'll say on a 1, it just looped itself. Right? Good old-fashioned state machine. And it's deterministic. What do we mean by deterministic? That means if I tell you what state you're in, and I tell you what symbol you read, then there's one and only one state that you'll end up in. There's no choice about it. If you're here and you read a 0, you have to be here. So your next state is completely determined by the input symbol. So section 1.2, we introduce nondeterminism. So in nondeterminism, intuitively, to appeal to your intuition, we're now going to give our machine a choice. It no longer has a strict path that it has to follow. And so here's an example of our first non-deterministic finite automata. So far we've been talking about deterministic finite automaton or DFAs. Now we're going to introduce non-deterministic finite automatas or NFAs, which is what I'll call them from here on out. So here we have an NFA. It has a finite number of states, so it's still a finite state machine, but it's non-deterministic. What do we mean by it's non-deterministic? If you're at Q1 and you read a 1, where do you go?
Q1 and Q2.
You could go to Q1 or you could go to Q2, right? You can go all over the place. So how do we determine the strings that a machine like this accepts? So a non-deterministic finite automaton, an NFA, accepts a string if there is any possible path that leads to an accept state. So let's do an example of that, and we'll build a little tree to the side here to help us in. So when we start our machine here, we start out in state Q1, right? And I'm going to read this string right here, 0, 1, 1, 0. You with me? When I read a 0, what are all the possible states I could be in?
Q1.
Just Q1. So on a 0, we'll make this a little tree, but say what we read there. On a 0, we could only be in the state Q1. Okay, now what about on a 1, where could I be?
Q1 or Q2.
I could be in Q1, I could be in Q2. Now, this epsilon symbol means reading nothing, we can go to Q3. So I could go to Q1, I could go to Q2, or I could go to Q3 on a 1. So from here, on a 1, it's possible that I could go back to Q1. On a 1, it's possible that I could go to Q2. And on a 1, it's possible that I could go to Q3.
Wouldn't you have to add those 3 to the top one as well?
No, this is where I was reading each input.
So you did read
Q1, I read 0, I'm now at Q1.
Alright.
Q1, reading a 1, I can now be at Q1, Q2, or Q3.
And Q3 is not attached to Q2 in this case.
No, they're separate states. It's just possible to go from Q2 to Q3 reading nothing. It is not possible to go from Q3 to Q2 reading nothing.
But you can, but you can skip Q2 and go straight to Q3.
Sure, if that's how you want to think about it.
Okay.
On reading no more input, I can go from Q2 to Q3. Okay, so far we read 0, 1, now we're going to read 1 again. On a Q1, if I'm at Q1 and I read a 1, where are all the possible places I can go? Q1, Q2, Q3. So this one, once again, we could go to end up at Q1, Q2, Q3 on a 1. Q2 on a 1, where could I possibly go?
Nowhere.
Nowhere. So we're dead in the water there. On Q3, where are all the possible places we could go on 1? Q4. Right? And now, finally, we read our last input symbol, 0. If I'm at Q1 and I read a 0, where do I go? Q1. If I'm at Q2 and I read a 0, where do I go?
Q3.
That was on 0, that was on 0. Q3. If I'm at Q3 and I read a 0, where do I go?
Nowhere.
Nowhere, so that one's dead in the water. And if I'm at Q4 and I read a 0, where do I go? Q4. So these were all the possible paths I could have taken reading this input stream. Right? Do any of these paths have me end up in an accept state?
Yeah.
Yes, the last one. That's an accept state. So, we accept this string. If there's any possible path that leads to us accepting the string, then we accept. And so we kind of think about NFAs as trying all possible paths in parallel. And if any of them accept, it accepts.
So it loops through 1 and 2.
Or we can think about the machine as somehow guessing which choice to make, but it always guesses correctly. So if we had a machine that could always guess correctly what to do, what strings would it accept? Those are the strings that that machine accepts.
So it tries both, essentially, when it gets a 1. It would try 1 and 2.
That's what we need to think about. Programmatically, how would you run it? You would construct this tree, and then you check if any of the leaves of your tree were an accept state.
Okay.
But intuitively, that's what happens. Okay? Now, we hardly ever have to actually build these trees. Usually you can see, pretty much just by looking at it, for most of our simple examples, whether or not it ends up accepting.
I'm still a little bit confused of why Q1 goes straight to Q3 when Q3 comes from Q2.
This was a 3. Q1 on a 1.
Yes.
So if you only read a 1, there's 3 states you could possibly end up at. Only reading a 1, you could end up at Q1. Only reading a 1, you could end up at Q2. Only reading a 1, you could end up at, to get from here to here, we read a 1. To get from here to here, we read a nothing. So total, we read a 1.
It just seems like an odd way to write it. You might as well just put Q down to Q3, then over to Q4 on its own separate path, rather than go through Q2. It's just a really odd way of doing it. It's just, I don't know.
I don't know what's odd about it. Because one of the nice things about NFAs is, while it might be a little confusing to figure out exactly which, well, first let's read some of these strings and then I'll make my point about NFAs.
Okay.
So this string we accepted. Okay, let's look at this next string. Do we accept this string?
Yeah.
We do? Let's see. We could go 0, 1, 0, 1, 1, right? So notice that time we didn't use the empty transition here. If we would have tried to use the empty transition there, we would have been dead in the water. If we would have done reading 0, we end up here. Read 1, we end up here. Then if we try reading a 0, we're dead in the water. So it is giving us something by having that empty transition.
Wait, so if you get a dead in the water, then it doesn't matter what numbers come after it's on?
Yeah, dead in the water we reject. If you're here, the only input you can accept is a 1 from Q3.
So if you got a 0 and then a 1, it doesn't count.
If you had a 0 then a 1 at Q3, doesn't count.
Okay.
So when we had a deterministic machine, I erased it, shoot. Then we had a 0 and a 1 leaving every state. And 1 and only 1. 0 and 1 and only 1, 1 leaving every state. So you knew exactly what to do on every input. Here we don't even bother putting inputs that we don't care about. What do you do on 0? You die. Nothing. if you're in Q3.
Okay.
Okay? So we're just looking for possible paths that accept the string. Okay, so let's try this string. Do we accept this string?
No.
No? So 0, we end up here. 1, we end up here. 4 here. 0, we're still going this one. That gets us over here. Then 0 again. Yeah, we're dead. So there's no possible way for us to accept that string. What about this one?
Yes.
Yeah?
Uh-huh.
So Q1 on a 1, where do I go?
Q1.
Rotate it.
Q1.
And then go 0 again, rotate.
0, 0,
And
1,
Empty.
1. Perfect. Okay, so now looking at N1, what strings does it accept? Can you say it out loud? Can you vocalize what the strings are?
2 1s next to each other.
If it has 2 1s next to each other, it accepts. Is that the only strings it accepts? Let's try this one. 0, 1, 0, 1, 0. Will it accept this one?
Yeah.
Yeah, it will. 0, 1, 0, 1, 0. So what are all the strings that this machine accepts? Can you say it out loud?
Anything that isn't in 3 zeros.
Does that end in 3 zeros?
No.
What strings does it accept?
The first 2 ones aren't separated by 3 zeros.
You gotta get really specific. It accepts all the strings that have this as a substring or this as a substring. So if it contains a 1, 1 or a 1, 0, 1, this machine accepts. Otherwise, it rejects. And now that I tell you that, you can see how that's kind of written out right here. To get from here to here, what do we have to have?
2 1s.
We have to have a 1, and then a 0 or nothing, followed by a 1. So we can have a 1, nothing 1, or a 1, 0, 1. And those, we have to have those substrings to get from here to here. Outside that, we don't care. Does that make sense?
Yeah.
And while that seems, the first time you see NFAs, it kind of feels like it's harder to figure out which strings they accept. But oftentimes you can actually write machines where it's much clearer what they accept when you write it as an NFA versus a DFA. So if I were to try and write this thing as a DFA, a deterministic finite automaton, it would blow up into a mess.
Aren't they the same thing except with NFAs there's no...
If I did this as a DFA, I'd have to have 16 states. And so it gets really hard to keep track of what's going on. We'll do an example with one here. We'll write this one out. Not 16 states, 8 states, but we'll do an example with this one here to show you why NFAs are so useful. But anyways, so there's our first NFA. There's giving you an example. And there's the intuition for when we accept. And I think you guys pretty much got the intuition right there, right? Okay. Let's do a slightly more complicated NFA, one where it's a bit hard to see what exactly is going on, and I just want you to tell me yes or no if it accepts a string. So here's our machine. Our language now is AB, right? Here's the machine, here's our start state, here's our accept state. Let's start with the string AB. Does it accept AB?
Yes.
What? Oh. There's 3 states.
Yeah, but there's an empty.
There's an empty, you
Oh.
got it. From Q1 to Q2 on an A, and then when we read a B, we go to there, and then get to our accept state on the empty transition. So we read an A, a B, and nothing. Total, we've read AB. So yes, this one. Trying to do a Y. a weird angle. Yes, we accept that one.
Okay.
All right, so let's try again. What about AA?
No.
No.
AA, definitely not. If we don't have a B, we can't get past this point. So that one's a no. What about ABA?
Yes.
Yes.
Yes, that one we accept. ABA we accept. Okay, what about ABB?
Yes.
No.
Yes.
Wait, yeah.
ABB?
Where's the B?
Oh, that's
So
right.
I'll start out at Q1, tell me where to go on my A.
Q1.
Q1, tell me where to go on my B.
Q2.
I can't.
Oh, I got the arrows wrong. Okay. Never mind.
All right. So can I accept ABB?
No, you can't.
Okay, so this one's a no. All right, what about BAA?
No.
No?
Can't do
There's
anything
no way
with
for
B.
B to go.
Yeah, we can't start with a B, otherwise we're dead. The only thing we know how to start with is an A, so that's a no. What about AAAA?
No, you need a B.
We have to have a B somewhere, otherwise we can't make this transition. No. What about BA?
You can't start with B.
Can't start with a B. Perfect. What about BB?
Can't start with B.
Can't start with a B. What about AAABA?
Yes.
You sure?
No, it dies. Wait,
No,
no,
it
no, no,
is-
you
it is-
repeat itself multiple times.
Yeah, just repeat
And
it.
then you jump one time, then go to B, then, okay, yeah, so it works.
Yes, it works. Okay. So that one, I don't care as much if you can't put in words what exactly that one's doing. The point there was hopefully one that was hard for you to put in words, and so you had to think through each individual string.
Isn't that like if it has a subset ABA for exactly AB?
Now,
What is it?
well, first off, that didn't specify that it has to start with an A.
It just has to have an A and then.
And it has to start with an A.
It has to start with an A,
Has to end with an
right?
AB.
A. Oh, it can end with a 0 or nothing.
And its ending has to either be a B by itself or a BA.
So it could be an A.
So it has to start with an A. Might have some other things in between
And
there.
then it has to have a B.
Has to end in a B or a BA. That has to be its ending.
What if you have multiple B's in the middle? Like 3, well, yeah.
Yeah, what if
Okay,
two
so
B's?
if you.
It can't have two
And
B's.
then every B has to be followed by an A unless it's the last B. So that's probably the best way to say it. Starts with an A, and every B has to be followed by an A unless it's the last B. And that, I think, covers it.
So if you end up on a set state and then you input another language or
You're dead.
letter, you die and you're not accepted.
Correct.
Okay.
Perfect. All right, so let's do another example now. And now we've done all that, hopefully you can kind of figure out what this one's doing. So we're back to zeros and ones. 0 and 1, you can stay here as long as you want. But to get from here to the end, you have to read a 1, then a 0 or a 1, then a 0 or a 1. So how could we put that one in words?
It has to there has to be one second from the last or something like that.
Third from the last, right?
From the last. Yeah.
Your third to last character has to be a 1.
That's it.
That's it. That's the strings. Okay, so now we're going to create a DFA which does this. Going back to old style machines that we've been talking about. And here's the way I wrote out these states to help us think about it. I'm going to put 3 subscripts there. This represents the last 3 characters that we've seen.
Okay.
So this state is our last 3 characters are 0, 0, 0. This is our last 3 characters are 1, 0, 0. This is 0, 1, 0. This is 1, 1, 0. This is 1, 1, 1, etc. There's 8 possible ways. There's 8 binary strings you can make with the number 0 and 1. If you're using 3 digits. If I'm using 3 digits, there's 8 possible ways I can fill that out with zeros and ones. I have 2 options for what goes there, either 0 or 1. 2 options for what goes there, either 0 or 1. 2 options for what goes there. 2 times 2 times 2, 8. So we have 8 states here. With me?
Mm-hmm.
Okay. So now, here's our start state. We pretend that our last 3 strings were all zeros. 0 we can just think about as representing not 1 here if we want. Or you can think about it as actually 0. Either way is fine. Okay, so now we'll start at our last 3 characters were 0, 0, 0. If I read a 1, what now are my last 3 characters?
0, 0, 1.
0, 0, 1. So on a 1, I come down here to 0, 0, 1. On a 0, what are my last three characters?
Stays.
0, 0, 0 still. Okay? 0, 0, 1. If I read a 1, what are my last three characters?
0, 1, 1.
0, 1, 1. So that's, sorry, let me shift that up a little bit. Oh, I forgot what the subscript was there.
It was 1, 0, 1.
1, 0, 1. Okay, take your word for it. We'll figure out if we were wrong. So 0, 1, 1, on a 1 goes over here, right?
Could you remind me what we're doing? I'm not following.
These are the last three characters that we've seen of our string so far.
Okay.
So if my last three characters I've seen so far were 0, 0, 1, and then I read a 1, then now my last three characters are 0, 1, 1.
Okay.
We're only keeping track of the last three things we've seen.
Okay.
So we're starting out assuming that the last three things we've seen were all 0. In other words, things that we're not going to accept. We only want to accept if we have a 1 in this position. If it's 1, something, something, then we accept.
Okay.
Or in other words, your third to last character is a 1. Everyone with me on the thinking of how we set this machine? And then the order I laid them out in, that's just so that the arrows don't make too big of a mess. So there isn't really a logic to the order except that I already knew the picture at the end. And so trying to make it not a nightmare of a bunch of crossing arrows. All right, now on 0, 0, 1, when we read a 0, where do we go?
0, 1, 0.
We're going to go over here, right? Let me write these closer to where they come out so we can keep track of them there. Okay, so we've done that one, we've done that one. Let's do this one. On 1, 0, 0, if we read a 1, where do we go?
0, 1, 0.
Oh, 0, 1, 1.
0, 0, 1, right?
Yeah.
Oh,
So far we've read 1, 0, 0. If we read another 1, then now our last three characters are 0, 1, 1. So now our last three characters are 0, 1, 1. So on
0,
1, we go there. On a 0, where do we go?
Go back to the start.
First.
We go to the start state. So if we have a 1, 1, 0 as our last three characters, or I read a 0, now my last three characters are 0, 0, 0. Okay. Now let's do this one. 1, 0, 1. On a 1, where do we go?
Watch me, right? 0, 1, 1.
We go to 0, 1, 1. Right? So that was, we are at state 1, 0, 1. If we read a 1, then our last three characters are 0, 1, 1, this one. And if we read a 0, then our last three characters are 0, 1, 0, which is this one. Right? Okay? So we did that one, we did that one, now it's this one. So if our last three characters are 0, 1, 0, and if we end it in a 1, then we go to 1, 0, 1. So 1, 0, 1's right here. So let me move that arrow a little bit. Make this arrow curve a little. You on a 1, come back here. And on a 0, we put a 0 there. Our last three characters are 1, 0, 0, which is over here. Right? Now, if our last three characters were 1, 1, 0, and we read a 1, we need to go to 1, 0, 1. 1, 0, 1 is right here, so this one comes through to this one on a 1. And then if instead we would have read a 0, so we got 1, 0, 0. 1, 0, 0 is right here, so this one on a 0 comes to this state. Now finally this one, if our last three characters were 1, 1, 1, and we read a 1, then we stay here. And if we read a 0, then we go to 1, 1, 0, which is over here.
That's 0, 1, 1.
Oh, thank you. 1, 1, 0. We go to here.
We didn't draw 0, 1, 1 either, where it goes to.
And we didn't do this one. So 0, 1, 1, on a 1, it goes over here. And on a 0, it goes over here, right?
Yep.
Okay. Now, which states are our accept states? Any ones that have a 1 in the third to last position. So if my string ending is 1, 0, 0, we accept. If my string ending is 1, 0, 1, we accept. if my string ending is 111, we accept. Sorry, didn't make it very clear. And if it's 110, we accept. And that's all of them, right? There should be 4. 1, 2, 3, 4. Okay. Now imagine I gave you that DFA, but instead of my states being labeled like this, I labeled my state Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, and asked you what that DFA was doing. You would be at a huge loss, and it would take you a considerable amount of time to figure out what on earth it's doing. And yet this one right here, it's perfectly clear what it was doing.
Yeah.
They're logically equivalent. This is why we love NFAs so much.
Simplify it.
They help us communicate very clearly. So it makes it a little bit harder to determine whether or not a particular string is accepted, maybe, because we have some choice there. But when we're communicating a language, it's a lot easier to talk about the language of this machine than the language of this machine, even though they're identical. Make sense? So that's a big motivation. Now we will prove that every NFA can be converted into a DFA, and so an NFA isn't in any way more powerful than a DFA. If I can build an NFA to recognize some language, I can also build a DFA to recognize that language.
Do you do it vice versa?
Every DFA is already an NFA.
Every determinant is already non-determinate.
Every deterministic finite automata is already a non-deterministic finite automata. We don't have to put choices in there. We just can put choices in there.
So why isn't every non-determinate determinate?
A deterministic finite automata can't have choices. A DFA cannot have choices. An NFA can. It doesn't have to, but it can.
Oh, I see what you're saying.
So a DFA is automatically an NFA.
Yeah.
The question is an NFA somehow more powerful than a DFA? Can it somehow recognize languages that a DFA can't? And the answer turns out to be no.
So it's like a subset.
They're not subsets, they're equivalent. An NFA is equivalent to a DFA. That's what we're going to show.
But all DFAs are an NFA.
All DFAs are NFAs. Okay, in that sense, yes, subset.
Are you saying all NFAs are DFAs too?
I'm saying if I can create an NFA to recognize some language,
Okay.
I can also create a DFA to recognize a language. What we're actually interested in are the languages that can be accepted by machines. So we went over a language last time that you couldn't create a DFA to accept. We talked about the set of all strings, 0 to the n, 1 to the n, where n is a natural number. Now I haven't proved it to you yet, but you cannot create a DFA which accepts those strings.
Therefore, an NFA can.
Right? And you might be tempted to think, well, maybe an NFA could. We're going to show that every NFA is logically equivalent to a DFA, and therefore no NFA could recognize that thing, that language. So NFAs cannot recognize languages that DFAs can't recognize. They recognize the same languages, and therefore they're the same powerful. We think about how powerful a machine is in terms of the languages it can recognize. It takes a more powerful machine to recognize these types of languages. And we'll talk about those in section 1.4, but suffice it to say, 1.4, maybe later. Now we can't do it. So NFAs, they have their advantages, they have their disadvantages. It's just a matter of when they're useful, but they're just as powerful. So if you use an NFA instead of a DFA, or a DFA instead of an NFA, there's no cheating going on. They're logically equivalent. So you just use whatever makes more sense. With me?
Yep.
Okay. Now, let's construct a little NFA here. And one that we already showed how to construct a DFA for last time. So last time we talked about how we could create a DFA to recognize the union of two languages. We said if language A1 is regular and language A2 is regular, and we built the machine to recognize A1 and we built the machine to recognize A2, we talked about how you could build a new machine to recognize the union of both those languages. You remember that? We still have it scribbled up right here. Here was our first machine, M1. Here was our second machine, M2. This recognized all the strings that have what is it? An even number of zeros. This recognizes all the strings that have an even number of ones. This recognizes all the strings that have an even number of zeros or an even number of ones. Right? So we're going to do something similar here now. So our language now is going to be a unary language. Only one term in there, just 0. Not 0, 1, just 0. Okay? And our job is to find an NFA or construct an NFA, a non-deterministic finite automata, such that its language is all the strings 0 to the k, where k is divisible by 2 or k is divisible by 3. So we want it to accept this string because there's 2 zeros in there, and 2 is divisible by 2. We want it to accept this string because there's 4 zeros in there. 4 is divisible by 2. We want it to accept this string because it's 6 zeros, and 6 is divisible by 3. So if the number of zeros we write is a multiple of 2 or 3, we want to accept. We would not want to accept this string because it's 5 zeros, and 5 is not a multiple of 2, and 5 is not a multiple of 3. Sorry, might not be used to notation here. So 0 to the k, if I put 0 to the 5 in this context, 0 to the 5, that just means 0, 0, 0, 0, 0. That's what we mean by that. 2 vertical line k, that's a statement. That says 2 divides k, or 2 goes into k evenly. That's the logic symbol for or, and this says 3 divides k. So we're looking for all the strings of zeros where the length of 0 is a multiple of 2 or a multiple of 3. That's what this is saying. Everyone understand what we're trying to construct?
Yeah.
So let's do it easy. Let's first construct all the ones that recognize a multiple of 2. And then we'll do ones that recognize a multiple of 3. And then we'll put them together. We'll union them together. You with me?
Yeah.
So let's start with all the multiples of 2. Zeros. So I start here in this state. We'll call it Q1, why not? We'll call this one Q2. We're looking for a multiple of 2 on our zeros, right? So on a 0, I go over here, and then on a 0, I may go back. This one is the multiple of 2 state. Here's our start state. This one's the multiple of 2 state. We've seen 0 zeros. Now I've seen 1 0. Now I've seen 2 zeros. Now I've seen 3. Now I've seen 4. Now I've seen 5. Now I've seen 6, etc. So anytime we've seen an even one, we end up in this state. Remember that 0 is even. So run 2 circles first. So this is a machine that recognizes strings of zeros where the number of zeros we've seen is a multiple of 2, right? Now let's do one where the number of strings we've seen is a multiple of 3. So the start state will also be the accept state, same as before. I'll start that at Q3. That's our start state. We're going to have it go to Q4, Q5, and then back over here Q6. Or back. So 0, 0, 0. So we've seen 0 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So we end up here anytime it's a multiple of 3. Now, the way that we built the machine over there is we kind of ran both machines in parallel. And so if I want to run both these machines in parallel, doing what we did over there, I'll have to construct a new machine with 6 states. And I'd have to have the state Q1, Q3, the state Q1, Q4, the state Q1, Q5, the state Q2, Q3, the state Q2, Q4, the state Q2, Q5. And I'd have to rethink about how all the connections would go. Same thing we did over there, right? With non-determinism, this problem is so trivial, we hardly even have to think about it. All we do now is we add a new start state. We call it Q0, right? Here's our new start state. And we transition over here on an epsilon transition, and we transition over here on an epsilon transition, and we make this one also an accept state. Right? So now we start this machine reading nothing, and if this machine ends up accepting, we must have been a multiple of 3. We can also transition here with nothing, And if this machine ends up accepting, it's because it was a multiple of 2. So on multiples of 2, this path will always accept. On multiples of 3, this path will always accept. And so now we built an NFA that accepts the union.
But he doesn't have to. Okay, so if you were left.
I don't even think we had to make this one accept state. I got thinking of something else.
Well, well, that's true. You don't.
It can be an accept state, but
What if you get the
in that example, it could have been an accept state.
Okay.
If you get just the empty string, then you're right there, you accept.
Okay, but then if you pass in 0, then pass in, okay,
If you pass in 0,
then you would be
if you pass in 0, then you would be at Q1 or Q4.
okay, now pass
Reject.
in another 0.
Passing in another 0, now you'd be in one of these two states.
Okay, because you're on a single accept state, does that not make it true?
Yeah, so it would accept this string. Is the number of zeros in this string a multiple of 2 or 3?
Or, okay.
Or.
Got it.
Or.
Yep.
So nondeterminism works really nice with ors. Alright, that one makes sense? And everyone see how that's way simpler than what we did over there?
Is 0 a multiple of 3?
Yes. What does it mean to be a multiple of 3? It means some integer times 3 gives you the number. Can I find some integer x such that 3 times x is equal to 0? There's some integer that makes that true?
Yeah.
Then yes. So if I can find any x that makes a statement true, for some number a over here, if I can find some x that makes a statement true, for some number a, then a is a multiple of 3. If 3 times some integer gives me my number is a multiple of 3. Okay. Alright, so now I think we're ready for the dense, full definition of what exactly an NFA is now. Now we got our intuition for it. And we're going to see that it's almost identical to a DFA. The only thing that really changes is the transition function. So, an NFA is a 5-tuple, just like a DFA was. This is our, what's Q going to be?
The set of states.
Our states. What's sigma going to be?
Alphabet.
Our alphabet. What's delta going to be?
Function process.
Transition function. Q naught's going to be
Start state.
start state, and F is going to be
Accept state.
our set of accept states.
Yes.
Not necessarily singular. All right, so NFA, same thing. An NFA is a 5-tuple Q sigma delta Q naught F, where Q is a finite set of states, sigma is a finite alphabet, delta now is a transition function who takes as an input some state along with some input alphabet or the empty string. Remember this symbol? Sigma with a little epsilon down there? So if sigma by itself was the set 1, 2, then sigma sub epsilon is 1, 2 epsilon. So in other words, an epsilon is always a valid character to use in an NFA. Coming back over here, the language of our machine was just 0, 1. But we were allowed to use epsilons in our transitions. So epsilon is not in the language.
So if you were to create DFA of that and one, then it wouldn't have the epsilon symbol?
Exactly. Notice that there's no epsilons in here. Well, I guess there weren't in here either.
Yeah.
Sorry. I should have thought about that before I created my example. But yes, if this one did happen to have some epsilons in here, by the time we came down here and we wrote it all out, all our epsilons would be gone.
You don't need epsilons in your NFAs, right? Like you could remove your epsilon out of.
You don't have to have them. No, I can't just remove this. That changes the actual machine.
What if you just put
Because now it doesn't accept strings with substring 1, 1.
But if you
You
put
put
one down,
one
it
from
kind of
Q1 to Q3.
Oh, there's ways that you can get around it, sure.
Okay, all right.
But yeah, you can't just go around removing them. There's ways that you can patch it up. And yes, that's always the case. Because you can ultimately keep patching it up to the point where you get rid of all the non-determinism and you're left with the DFA.
All right.
And the epsilon transitions are part of the non-determinism. Okay, so notice that our alphabet here, the alphabet of our machine, does not have epsilon now. Our transition function can take an epsilon for a transition. The alphabet of that machine is just 0, 1, but it can still read an epsilon. So our transition function is allowed to read epsilons. So our transition function takes a state and some input symbol, or epsilon, and now it spits out, it doesn't spit out a state anymore, it spits out a set of states. So back on this machine, when it read a 0, it spat out Q1, but when it reads a Q1, it spits out the set containing Q1, Q2, Q3. So this machine, when it read a 0, it spat out the set containing Q1, and when it read a 1, it spat out the set containing Q1, Q2, and Q3. Does that make sense? Because there's multiple states that you could potentially be in. If I give you a state and an input symbol, your output is a collection of states, not just a single state. Sorry, did we ever go over the power set?
That makes more sense what you mean by begin.
No, we didn't do the power set. Sorry. That should have been done in the preliminaries, and I forgot to do it. Right. Pause. Power set. Power set is the set of all possible subsets. So let's go over this in some simple cases. So I'm going to write the power set of the set containing 1. This is equal to the set containing, what are all the possible subsets of the set containing 1?
Empty 1.
The empty set and the set containing 1. Notice that the empty set is a subset of the set containing 1, and the set containing 1 is a subset of the set containing 1. So the power set of the set containing 1 is the set of all possible subsets. Let's try out another one. Let's do the power set now of the set AB. What are all the possible subsets of the set AB?
Empty set.
We could have the empty set, we have the set containing A, we could have the set containing B, and we could have the set containing AB. That's a possible subset, that's a possible subset, that's a possible subset, that's a possible subset. Those are all the possible subsets. Right? One more, just to be super clear, and then we'll call it good. 1, 2, 3. First off, how many possible subsets am I going to have?
6,
8. Nice try.
8.
So let's write out all 8 of them. We can have the empty set, we can have the set containing 1, we can have the set containing 2, we can have the set containing 3. 3s are hard when you're writing sets. We can have the set containing 1, 2. We can have the set containing 1, 3. 1, 3. We can have the set containing 2, 3. And we can have the set containing 1, 2, 3.
And it's 2 to the power of the number of
Yes.
elements.
So since this was an n element set, its power set has 2 to the n elements. This had 3 elements, this has 2 to the 3. This had 2 elements, this has 2 to the 2. This has 1 element, this has 2 to the 1. Okay, so that's the power set. So what this is saying is, on a non-deterministic finite automata, on an NFA, when you're at some state, like Q1, and you read some symbol, like 1, so the transition function here, let's write out exactly what it did. We'll call it delta. Delta here, on Q1, when you gave a 1, was equal to the set Q1, Q2, Q3. At Q1, when we read a 1, the 3 possible places we could end up were Q1, Q2, Q3. So delta of Q1, when you give it a 1, is the set containing Q1, Q2, Q3. And notice that this is a subset of Q. What's Q? Q is the set containing Q1, Q2, Q3, Q4. So when we do a transition on an NFA, we'll end up in some subset of Q, where Q is the set Q1, Q2, Q3, Q4, the set of all states.
So the power set.
Notice that the power set always includes the empty set. So if I were at Q3, so delta here delta on Q3 and 0 is equal to the empty set. If I'm at Q3 and I read to 0, there's nowhere I can go. Here's a set of all the states I can go to. I can't go to any.
So number 3, the power set is saying just take one set from the power set.
Remember what this function says. This function notation. That's why it was crucial that you get this. And I know it's dense. There's a lot going on. When you see some function, let's see it in a more simple case for a second, just to help you remember. When you see f is a function from a to b, what does that mean? That means f is a function whose inputs are everything in a and whose outputs are some subset of b. Right? Now, our case, we have delta is a function from q cross sigma epsilon. So we could be, our input could be any state along with any input symbol, and our output is the power set of q, right?
Which is a subset.
No, so delta will always spit out a subset of this thing, or an element in this thing, I mean. The image of delta will be a subset of this thing. Each individual output is an element of this. Each input is an element of this. Each input is one state with one symbol, and each output is one subset of all the possible subsets of Q. So each input is one thing in there, and each output is one thing in there. Each output is one thing in this set. It's either that, or 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 that. Those are the possible outputs. And it gets confusing because the output is a state. The output here is a state, not a state. A set. The output is a set of states. And that can get really confusing.
Oh, because of the power set.
The power set is a set of all possible subsets. When you run delta on the function, you're going to get some set over here. And whatever that set is, it will be a subset of the set containing Q1, Q2, Q3, Q4. It will be a subset of Q, where Q is a set of all these states.
That's cool.
The output is still set with DFAs, right?
In DFAs, so for a DFA, our transition function looks like this.
Yep.
Your input symbol couldn't be epsilon. And your output was always just a single state, not a set of states.
But isn't that term saying function from A to subset of B?
So delta maps everything in here to something in there. It may not use all of Q. In other words, I can create my state machine to look like this. Let's go back to the even number of zeros. I can create it like this. 0, 0, this is also my accept state. 0, 1, 1. And then I could have also put a state here, which goes over here on a 1, goes to itself on a 0, and this loops itself on a 1 or a 0. Okay, that's completely useless. But I can still add it,
Yeah.
right? I guess that doesn't really get to the point I was even making. Sorry, back apple. Should have said that. In this case, it will always, for our machines, it will always be the case that we use all of Q. That's what I should have said.
Okay.
And that other example probably just confused. Sorry.
But it's still set even if we're going to use all of Q.
Even if we use all of Q, it still maps everything in here to something in there. When we're talking about each individual mapping, we take an element from here and we map it to an element in there. An element of Q is one state. An element of the power set of Q is now a set of states. Because this is now a set of states. Q is just a set of states. The power set of Q is a set of states. It's just like this right here. This set right here is a set of integers. This right here is a set of integers. Q is a set of states. The power set of Q is a set of states. And once you get your head around that, you got your head around the hardest part. I think. We'll see. Okay, so back to definition. And I think you got the transition function now. The transition function maps every state and some input symbol to some set of states. As a transition function, Q naught is just a start state, and F is a subset of Q is the accept states. So same as before, the only thing that changes is our transition function. Everything else is the same. Make sense? Alright, so now let's move on to write this out explicitly. The same way that we wrote some DFAs out explicitly. Let's write N1, N2, and N3 out explicitly, just to make sure we understand. So N1, that's this one right here. Notice that these are named. N1's right there, N2's down here, and N3 is this one. So starting with N1, let's write that one out. So N1 is equal to, what is my Q?
Q1, Q2, Q3.
Q1, Q2, Q3. Is there 4 of them?
Why not Q4 again?
Okay. So there's our set of states. What's my alphabet?
0 and 1.
0, 1. Delta, we'll write out delta separately as a table. We'll use tables for our functions now rather than writing them out as sets of ordered pairs. But hopefully you still have in mind a function is always just a set of ordered pairs. Don't lose track of that. What's our start state?
Q1.
Q1. And what's our accept states?
Q4.
Just Q4?
Yeah.
Okay, so N1 is that 5 tuple, where delta is given by this table, and we'll write our table over here. So delta, our inputs are states and symbols. So all our possible states are Q1, Q2, Q3, Q4. All our possible symbols are 0, 1, and epsilon. Don't forget the epsilon. Okay, now Q1 on a 0, where can I possibly go?
Q1.
Just Q1?
Yep.
Okay. Q1 on a 1, where can I possibly go?
Q1, Q2, or Q3.
Yeah, space these out more. Put 1 there, epsilon there.
Is it a given that all sets have epsilon inside their set?
No, no sets have epsilon inside of sets unless it's explicitly stated.
Okay, so inside of your 5 tuple or whatever, you have the alphabet as 0, 1.
The alphabet is only 0, 1. Back to our definition. Notice that our NFA is this 5 tuple, Q sigma, but our transition function uses sigma sub epsilon.
So should we have not included?
So our alphabet is just 0, 1, but our table is allowed to also make epsilon transitions.
So should we have not put Q3 in under 1 for Q1? Because it technically takes an epsilon then.
Now, just reading a 1, here's where we could get to.
Then why do you have epsilon there?
You'll see.
Okay.
Q1 on just reading an epsilon, where can we go?
Nowhere.
Nowhere. So we go nowhere. So that's the empty set. All right, next. Q2. When we read 0, where do we go?
Q3.
So here we can only go to Q3. Q2 reading a 1, where do we go?
Empty set.
Nowhere. And then Q2 reading an epsilon, where do we go?
Q3.
And so you see it comes into play.
I just don't know why.
I don't know why it can't be considered part of the alphabet, is what's confusing.
Because when we reduce our NFA back to a DFA, we don't want to change the alphabet, because then we're changing the language of strings that we recognize. I mean, it really doesn't change the language if you do put an epsilon in there, because this string, 1, 0, epsilon, 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 1, epsilon, 1, is just a string 1, 0, 1, 1.
Okay?
So it just adds confusion.
Yeah, because there's an infinite amount of them, essentially.
So you can put the epsilon in the language, and it doesn't change the strings that you're generating. But that's a lot more confusing to read than just that. And so it doesn't really add anything.
So, reading based off of your 5 tuple, can we just like it? Well, never mind.
Okay, so Q3 reading is 0, where can we go?
You said it.
Nowhere. Q3 reading a 1, where can we go?
Q4.
Just Q4. And Q3 reading epsilon, where can we go?
And you said
Nowhere. Q4 reading a 0, where can we go?
Q4.
Q4 reading a 1, where can we go?
Q4.
And Q4 reading epsilon, where can we go?
And you said
Okay. And then you'll probably guess now, for bigger NFAs, most of our transitions end up going to nowhere, because we only put in the ones that we really care about. So it's also often commonly the case when you see these tables that all the empty sets, they actually just leave blank. So you see blanks there, it's implicitly the empty set. But there we go, so there's our transition function. It takes as an input some state along with some alphabet symbol along with the empty string, and it spits out some possible subsets of Q. Remember that Q in this example is Q1, Q2, Q3, Q4. Notice that everything here is a subset of that.
You can almost make these all their own function. Just maps, but never.
Well, that is a function. We're just trying it as a table. So there's our transition function
State.
for that machine.
Just to clarify, you could remove the rightmost column, epsilon, and it would still do the same thing as your picture over on the left.
Yes, but then it would, we might be, remember that you need to be able to go from this to the picture as well. And if I were to get rid of that column, then now you think, well, that is kind of confusing actually,
It just
because you
seems
can't.
repetitive.
It would be logically equivalent. But no, the reason that you can't just get rid of epsilons is because imagine writing it out for this ink. If you got rid of the epsilon transitions, now you're kind of stuck. Well, I guess it'd be like skipping ahead. Just makes it hard to reason about. Because if I get rid of the epsilons here, then I need to make this on a 0, go to right there. And I need to make this one on a 0, go to right there.
Right, it just seems repetitive to have three in both.
Again, we never actually have to have the epsilons because everything can be converted to DFA.
Right.
The advantage is, in looking at it, it helps us reason about the language. So we don't have to have NFAs, they're just useful to have. And the epsilon transitions are useful because then we can just union two machines like this without hardly having to think about it. And so we can actually start writing procedures for how exactly we union these things together. I can describe this as a procedure. If you want me to get rid of those epsilons, then I have to reason about the machine and think, okay, so then on a 0, which of these did I actually want to go to? So with the epsilon, I don't even have to reason about this machine. I don't have to know what these machines do. In fact, if you would have just told me there's some machine, here's its start state, and la-da-da-da-da somewhere along it accepts, and here's some other machine, here's its start state, and la-da-da-da-da somewhere along it accepts, and maybe it has a couple accepts, who cares? I can union them together, I can tell you exactly how to do it without knowing any of the details of the machine. I'm going to say start here, and do an epsilon there, and do an epsilon there, and there you go, there's your machine that accepts the union. So, just helps us reason about it. Okay. There we go. We wrote out N1. So now, let's do N2. Make sure we understand the definitions. And then maybe N3 is overkill. Maybe after N2, you guys will have it. So, let's write out N2. N2 is equal to, what are my states?
Q1, Q2, Q3, Q4.
Q1, Q2, same thing, probably should have left that. Q3, Q4. What's my language?
A, B.
A, B. And then delta we'll write separately as a table. And then my start state.
Q1,
And my accept states.
Q4.
Q. Okay, there's our machine. Write our table. Table. Q1, Q2, Q3, Q4, 0, 1, that's 1. All right, Q1 on a 0, where can we go? Or on A and B. A, B. Q1 on A,
Q1 or Q2.
Q1, comma, Q2. On a B,
Empty set.
for dead. On epsilon,
Empty set.
Q2 on an A,
Empty set.
on a B,
Q1, Q3, and Q4.
Q1, Q3, Q4. I'm wondering if I'm converting these right. Oh well, if I made a mistake, then we'll see it later. On the epsilon,
The empty set.
empty set. Q3 on A,
Q4.
Q4. On B,
Empty set.
on epsilon,
Q4.
Q4 on A,
Empty set.
Empty.
empty on all of them.
Yeah.
Oh, because that's the final one. Okay. And there we go. And I think you guys get it. Right? That's how we use the definition. Here's our function, transition function. Here's the definition of these machines. Okay. So now you have the intuition for when these machines accept. Let's get our definition for when these machines accept. You already got intuition for this? Now let's look at the definition. Let n be this NFA. Stats, language, transition function, start, accept. Okay. Then n accepts the string w, where w has n characters, and each of those n characters are in the language together with epsilon.
That a string couldn't have epsilon.
It can, it just doesn't change the string.
Okay.
So this string, 1 epsilon 1 is equal to 1, 1. So if my input string is 1, 1, this is a perfectly valid way to rewrite it. And if I rewrite it this way, it's going to help me make some of these transitions. 1, epsilon 1.
I thought sigma was the alphabet.
Sigma is the alphabet. Sigma sub epsilon is the alphabet together with epsilon.
So why do you keep saying language?
Did I say language? I meant alphabet.
Okay.
Okay. Yeah, make sure I say this correctly. So W is some string in the language. It's a bunch of characters.
Yep.
Each of these characters are either alphabet symbols or they're epsilon.
Yep.
So W could be the string 1, 1, or it could be the string 1, epsilon 1. Those are both fine. That's the exact same string. Okay? Okay, so our machine accepts the string W, expressed this way, where each one of those are characters in the alphabet together with epsilon, if there exists some sequence of states, R1, R2, all the way up to Rn and Q, if there exists some sequence of states such that 3 things occur. 1, the first state in our sequence, R1, is equal to, oh sorry, this should start at R sub 0. Remember, we need one more state, then we have input symbols, right? In order, if I have a machine, just keep it really simple. Q1, Q2, and it just accepts all the strings that have one character. We'll make this the accept and this is start. So it accepts all the strings that have exactly one character. Every string it accepts only has one character, right? But it has 2 states. If we did the one that accepted all the strings with 2 characters, then we'd have to go through 3 states. So to read 2 characters, we need to go through 3 states. To read n input symbols, we need n plus 1 states. So notice that this is 1, 2, 3, 4 all the way up to n. This is 0, 1, 2, 3, 4 all the way up to n. So we have one more state, and then we have input symbol here.
Wouldn't it be up to n plus 1? For the
No, I could have done 1 to n plus 1 or 0 to n.
Oh.
I chose 0 to n.
Okay.
So we just decrement to where we started. Okay. So we accept this input string if there exists some sequence of states where that sequence has one more state than we have input symbols, and that first state in our sequence happens to be the start state, and the next state in our sequence is always in the set of states that could have been reached from the previous state with the next input symbol. Go ahead and consume this line for a second, and I'll say it again, and it might make sense. Remember that our transition function for an NFA gives us a set of states. So this is a set of states. Delta of r sub I and w sub I plus 1. This is a character. This is a state. Delta takes a state and a character and gives you a set of states. We're saying that the next state is in the set of states that could have been reached from reading, or from this state reading this input symbol, where I iterates from 0 to n minus 1.
What is iterating?
Plug in 0. So if we plug in 0 for 1, then we're saying r sub 1 is in the state we can reach from r sub 0 reading the first input symbol. Now plug in 1. R sub 2, let me explicitly write some of these out. So I'll write out the case for I0, I1, I2, and then I think you'll get it. So we're saying R0 has to be in the symbols you can get to from R1, R1 has to be in the set of states you can get through from R0 reading our first input symbol. R2 has to be in the set of states you can get from R1 reading our next input symbol. R3 has to be in the set of states you can get from our next state R2 reading our next input symbol. So we start at R0. We read our first symbol, which is W1. W1 is our first symbol. R0 is our first state that we're in. And R0 has to be our first condition says R0 is our start state. Delta of R0 on W1 is a set of all the states we can reach from R0 reading symbol W1, right? So this is the set of all the states we can reach from R0 reading symbol W1. R1 better be in there if this is the sequence of states that we go through accepting the string. R1 has to be one of the states we can reach from R0 reading W1. R2 has to be one of the states we can reach from R1 reading symbol W2.
So ours are like
Etc.
actions.
They're the states that we're going through. R0, R1, R2, R3, R4.
What are the other ones?
W1, W2, what was our symbol here? 1?
Yeah.
W3, W4.
Okay.
And keep doing that until we get all the way down to what's our last state? Our n has to be in the set of symbols we can get from R of n minus 1, comma, W sub n. Right?
Yeah.
That's if you plug in n minus 1 for I. N minus 1 plus 1 is n. Plugging in n minus 1 for I gives us R of n minus 1. Plugging n minus 1 for I gives us n minus 1 plus 1 is sub n. Right? So this says we start the start state. This says every time we make a transition, it was a legal transition. And this one says, and we end up in an accept state. If we can find some sequence of states that satisfy these three conditions, then we accept. Over here, we found that sequence of states. So that sequence of states was Q1, Q1, Q3, Q4, Q4. That was the sequence of states that worked over here. Let's maybe write that one out explicitly, just to make sure it is super quick. So our string that we're talking about, we're going to use that string, what was it, 0, 1, 1, 0. So to be super clear, our string is W is equal to 0, 1, 1, 0. So W1 is equal to 0. W2 is equal to 1. W3 is equal to 1. W4 is equal to 0. In this case, n is equal to 4. So W is equal to W1, W2, all the way up to Wn. In our case, n is 4, since there's 4 characters in there. There's W1, W2, W3, W4. With me? Now, our sequence of states that we said shows that we can accept is the sequence Q1, Q1, Q3, Q4, Q4. You with me? There's our sequence of states. We're given these labels R0, R1, R2, R3, R4. Notice it goes from R sub 0 to R sub n. Is R sub 0 our start state?
Yeah.
Yeah, that satisfies the first condition.
How does it not be your start state?
Well, I could have randomly put a sequence of states here. Q3, Q1, Q3, Q4, Q4.
Oh, but it doesn't have to be accurate. This is, okay, yeah.
We're saying that if you can find a sequence that satisfies these 3 conditions, then the string is accepted. That's what it means to accept, is this sequence of states that you transition through exists. So the first condition is that R1 or R0 is our accept state. Yes, that's the case. Next step, step 2 is saying that is it true that R1 is in the set of states that we can reach from R0 when we read W1? Well, delta on R0 reading W1, that's delta on what is R0? Q1. What is W1? 0. And what are the set of states we get to from Q1 reading a 0?
Q1.
The set containing Q1. Right?
Yeah.
So is it true that R1 is in the set containing Q1? Yes. All right, now is it true that R2 is in delta of R1, W2? Well, I'm saying, is it true that delta is in Q1, comma, W2 was a 1?
Yep.
What's Q1 1 equal to?
Q1, Q2, Q3.
Q1,
Set.
Q2, Q3. Is it true that R2 is in this set?
Yep.
Yes. So far we're still good. Now we see, is it true that R3 is in delta on R2 and W3? And we'll see, yes, it is the case. And then we'll say, what about R4? Is that in delta of R3 reading W4? Yes, that is the case. That satisfies condition 2. Now condition 3 says, is R4 in your accept states? R4 is Q4. Is Q4 one of our accept states?
Yeah.
Yes. So that is how you would prove, if you want to rigorously prove, that that string is accepted by that machine. Now, we'll never rigorously prove it like that, but it's good to wrap your head around the definition. And that's what it means to accept. It's a mouthful. But once you see it, it almost just reads like English. Your next state is in the set of states you can reach from your previous state and the next input symbol. That's all it's saying. For all your states except the last state. Well, up to your last state, yeah. Depending on which, if you think about that state is iterating. Anyways, think you got that definition with the examples? It's dense, but I think we can do it. Okay, so now we'll go over to this whiteboard. Actually, gonna need this thing. Okay. So now we've showed some of the usefulness of NFAs and helping get you familiar with NFAs, what they can and cannot do. So now we're going to talk about how could we systematically convert an NFA to a DFA. And we're going to do we're going to do an example where we use a procedure that we're going to end up using in our proof, similar to what we did last week. Often that helps you understand the proof is first example going over the exact procedure. You with me? So first, let's do it and see what we do by hand. So here's our machine. 1, 2, 3. This is our NFA. And here's what it accepts. Well, and here's how it transitions. So first off, here's the machine. 1, 2, 3, A, B, etc.
Yep.
And let's write out the transition function explicitly. 1 on an A, where does that go?
Empty set.
1 on A goes to the empty set. Perfect. 1 on a B, where does that go? 2. And 1 on an epsilon, where does that go?
3.
2 on an A, where does that go?
2 or 3.
2 or 3. Uh, 2 on a B, where does that go?
3.
And then 2 on an epsilon, where does that go?
Empty set.
And then finally, 3 on an A, where does that go?
1.
Or 3. Perfect.
1 or 3. That's cool.
On a B, where does 3 go?
Empty set.
Nowhere. And then on a epsilon, where does 3 go?
Empty set.
Empty set. Perfect. Okay. So now what we did in filling out this table is what we're going to do with this DFA here. So here's our NFA. I'm going to construct a DFA. I'm going to label each of its states a possible subset of the states that this machine was in. And on each input symbol, we're just going to keep track of all the possible states that this machine could have been in. Because after reading some input symbol, it has to be in some combination of the states 1, 2, and 3. Here we're tracking every possible combinations. So then it will have to be in one and only one of these states. Any combination of states here is represented by one and only one state over here. If we could be in all 3 states over here, that means we're in this state here. If we died over here, that means we're in this state here.
Yep.
So we're going to just track everything that could possibly happen.
Okay.
You see that? And that's a big idea. Which states accept? All our accept states are the states who contain, what's the right way to say this?
Contains 1.
Take this set, intersect it with the accept state here, if that's not empty. If it contains one of this thing's accept states, then we accept. Since this thing only had an accept state of 1, then any one of these states that have a 1 in it, we accept from. Because then it could have ended up in an accept state. Because this is intuitively saying, so far we could be in state 1 or 3 on this machine.
Yeah, I see.
If we could be in state 1, then we could accept.
Is there a reason you wrote N for the DFA?
Yes.
Because that's just what you do for DFAs.
Because up till now, we've been using N for those machines. And then we use N for NFAs since nondeterminism and since N's right after N. So this is just a machine. This is a nondeterministic version of the machine. Okay, so let's fill it out. Maybe ask one of the trickiest questions at first. What's our start state in this machine?
1.
The set containing 1? This one?
Yeah.
It's actually 1, 3. There's our start state.
Because of that.
Because of the epsilon. Notice we can't have epsilon transitions over here.
I see.
Right? So just starting out without reading anything, where could you be so far? 1 or 3.
Yep.
So far you could be in 1 or 3. Okay, perfect. Now we'll just systematically go from each state, seeing where we could be starting up here. On the empty set, reading a 0, reading an A, where do we go? Nowhere. Back to the empty set. And on a B, where do we go? Nowhere. We're back to the empty set. So this just, move the M over here a little bit. This just loops back to itself on A or B, right? If you're dead, you're dead. You can't reassemble to become undead. All right. So now, what about if you're at a 3? If you're at a 3 and you read an A, where could you go?
1
1 or 3.
You could go to 1
or 3.
or 3.
So go to the right.
So you can go to 1 or 3. So the state you could go to is 1 or 3. So we put the A there. Notice that we do not also put an A going here. We're writing a DFA here. This DFA is tracking this NFA.
Yes.
Our NFA could have been in the state 1, 3. If it was in the state 3, it could be in the state 1, 3 reading an A. Good? And what about a B from state 3?
Empty set.
That goes to our dead state, right? Okay, now let's do the 1. On a 1, reading an A, where could we go?
Empty set.
Nowhere, so we're dead. And on a B, where could we go? Just a second 2. Alright, from, if we were in 1 or 3, and we read an A, where could we go?
1 or 3, just right.
We could go a 1 or 3. Could we go anywhere else reading an A?
No.
If we were here and we read an A, we're dead. And if we're here and we read a 3, then we're 1 or 3. So the union of the empty set, union with the second containing 1, 3, is the second containing 1, 3. So an A on 1, 3 just loops to itself. I'm not sure how much space I'm going to need, so I'm going to write the loop down here just in case. Okay, on a B from 1, 3, where could we possibly be?
Just the set containing.
Just the set containing 2. On a B, we go here. Okay? On just 2, reading an A, where could we go?
Just like 1, 2, 3. 1, 2, 3. Oh, sorry, just 2 and 3.
Just 2 or 3. So on A, we could be in state 2 or 3. On a B, where could we be?
3.
Just 3, right? Okay. From 2 or 3, on an A, where could we go?
This one's 1, 2, 3.
2 or 1 or 3. 1, 2, 3.
1, 2, or 3. We could end up anywhere on an A, right? On a B from 2 or 3, where could we go?
3 or SC7.
Just 3.
Just 3.
Okay. From 1, 2, on an A, where can we go?
2 or 3 or 1.
Reading an A.
How do you get into 1? Reading an A, so we're in 1, 2, and we read an A, where could we end up?
Yeah, flip. Yeah,
We
just-
could end up here or here.
Oh.
So 1, 2 on an A goes to 2, 3. So on an A, we come down here. On a B, where could we go?
2 or 3.
On 1, 2, reading a B, we could go to 2, 3.
So A, comma B.
Oh. And then finally, on 1, 2, 3,
Go back to yourself. All times.
You could just go to 1. Oh wait, no, I don't know. It goes back to itself.
sorry, I'm checking something.
1 or 2 or 3. Yeah. Go back to
Okay,
itself.
sorry. On 1, 2, 3, yeah, if 2, 3 on an A goes to 1, 2, 3, then definitely 1, 2, 3 on an A has to go to 1, 2, 3.
Oh, but it's not the same for B, is it?
B is just 2, 3.
B can go to 2, 3. Can't get to 1. Right?
Mm-hmm.
just make sure nothing obvious. I even made a mistake right there. Okay. Yeah, that's the way these things go. Alright, so you got a feel for how we can create a DFA to model an NFA. We just create a state for every possible subset of states over here, and then we're tracking all the states this could have been in over here. That's how we create a DFA, which models an NFA. So here was our NFA here. Our DFA here, notice Q was the set containing the empty set, the set containing 1, the set containing 2, the set containing 3, the set containing 1, 2, 3. Right? Q has 8 elements. The alphabet here is AB, same as the alphabet there. The start state here was 1. The start state here was, I messed up, 1, 3. And then F prime is the accept states here, where F prime is the set containing 1, 1, 2, 1, 3, and 1, 2, 3.
Why don't you just do F subscript 1?
Prime, you use 1s and 2s typically if you have more than one. If you just have one other that you need named, it's often the case that you use a prime. So, but the prime, it's similar to putting a subscript 1 on there. So don't let that confuse you. Sorry.
It's the same thing.
It's the same thing. It's just coming up with another symbol.
Okay.
So it's just another symbol. The same way that delta and delta sub 1 and delta sub 2 are different symbols, so are delta and delta prime. It's just a way of saying, I want to call something different, but they're very much related. This has nothing to do with like prime and calculus. Again, we reuse a lot of the exact same notation, so for a lot of things. Like when we did 0 to the 4 over there. Well, 0 to the 4, it's 0, right? It's not 0, 0, 0, 0.
I see, yeah.
So, yeah, you have to infer from context a lot of times what certain things mean. And F prime, unfortunately, is often used as a derivative as well. So, it's the way it goes. Anyways, and I don't think we need to fill out this table. I think we did it, right?
Yep.
We'd just be drawing that picture down there. But important to know that the inputs for over here are now all these states and those input symbols. Okay, so now here's our theorem to prove that every NFA has an equivalent DFA. Or in other words, every NFA can be converted into a DFA. That does the same thing. This DFA does the exact same thing as this NFA. They recognize the same language. One's no better than the other. Okay, so here's how in general we do it. Now we're coming up with a general procedure for converting NFAs to DFAs. If we can come up with a general procedure for converting NFAs to DFAs, then all NFAs are DFAs. Right?
Yeah.
And we already know all DFAs are NFAs. We got that for free.
Yep.
So that means that they're logically equivalent once we prove this. Does that make sense? Okay. So every NFA has an equivalent DFA. So we'll start with an NFA and we'll convert to DFA. So let n equal to q sigma delta q naught f be any NFA, where the language of that machine is the language A. When we say that the DFA is equivalent to the NFA, we mean that they recognize the same language. That's what we mean when we say that this and this are equivalent. They recognize the same strings. The language of the machines are the same. That's what it means for two machines to be the same.
Yeah, okay.
It has nothing to do with the picture you use to draw them, or how you label things. Okay. So we're going to construct M now. So we start out with N, exactly what we did before. We start out with this, we construct this. We're going to do the same thing in our proof. So let M be given. Now we're going to construct M equal to, and we're going to use primes. Q prime, we're going to have the same input alphabet, so that sigma is still the same sigma. Delta prime, Q naught prime, so we're going to have a different start. And F prime, we're going to have different accepts. The only thing that's the same in here and here is we have the same alphabet.
Is there a reason there's not alphabet epsilon on the NFA?
Go back to our definition of an NFA. There was no epsilon here, it's just our transition function was allowed to use epsilons.
I see, yeah.
Okay. So the language of this machine right here is still AB, but our transition function is allowed to use epsilons.
Does it, this second definition say that the strings recognized by this machine can include the character epsilon?
They can include the character epsilon. It's valid to have the character epsilon.
So how can your language have strings with the character epsilon, but yours-
Because the character epsilon doesn't change the string. You can remove the epsilons and it's the same string.
Okay, but where you define like the language recognized by N, that has strings that contain the character epsilon. It may contain this, right?
Right, so this accepts the string, let's just give them really quick. This accepts the string epsilon A, which is the same as just A. Epsilon concatenated with A is the same as just A.
You start at 1, right? If you,
Well, now notice over here, go to our start state, 1, 3, read A. Where do we go? Back to 1, 3. We accept. So this accepted epsilon A, and this accepts A.
but the NFA does not accept just A, does it?
It accepts just A because just A is equivalent to epsilon A. We can rewrite A as epsilon A, and then we can run epsilon A on our transition function.
Okay, but like our transition function says A leads to the empty set.
Our transition function, so our transition function starting on, we start from state 1, reading the symbol epsilon gets us to 3, reading the symbol A gets us to 1, 3, which will accept.
But just reading A gets you to the empty set.
Remember, if there's any way to read the string to make it work, and this is kind of like adding 0 to a number. We didn't change this string by rewriting it like this.
Okay, but our transition function does not accept A.
Our transition function does not accept A. Our transition function accepts epsilon A. And so there's a way of writing this exact same string such that our transition function accepts it. So we accept that string. You just have to write the string a little bit funky for our table to accept it,
Alright.
which is fine. But actually, 1 on an A, we still should have said, no, we were right, empty set. Technically, and you're going to see it in the proof, so I should have even technically said this first. First we read the symbol, then we do the epsilon transitions. So we don't do epsilon transitions, then symbol. We do symbol, then epsilon transitions if we want.
So it can only end up in
So we can't get back to 1 by reading just an A. We can get back to 1 by reading nothing and then an A.
But you
It's a
said-
technicality. Yes, if your input string was just an A, if I said, where can we get on just an A, then you are correct. We could get to a 1. Why could we get to 1? Because A is A. And so you have to read it, the input string this way. If you were to write it out over there, this is our W0, this is our W1. Or sorry, this is our W1, this is our W2. And that's the way we would have had to write the string to make it accept. If we would have just written the string this way, it wouldn't have accepted. So if there's some way that we can write the string with epsilons in there, so that it ultimately accepts, then we accept that string. And since this string is identical to that string, we say we accept it, rather than specifying we accept epsilon A. Because that epsilon is just specific to how we drew our machine. It doesn't change anything about the language we accept. And ultimately, we care about the languages we accept. So is a string A in the language we accept? Yes. You just have to write it a little bit funny to get our particular machine to accept it.
Okay, I see now.
Okay. Yes. It's a weird technicality. But a good one that we went over before we dived into the proof. So I'm glad you brought that up. Okay, so now let's go over our proof. We were constructing, so we start out with Q sigma delta Q naught F. We're going to construct M with Q prime sigma delta prime Q naught prime F prime. Okay, such that, let's set it up. What is our new set of states going to be? What are the states for this machine? The set of all possible subsets of the states of this machine. So if the states of this machine are Q, the states of this machine are the power set of Q. So we're going to set Q prime equal to the power set of Q. Rather than starting at Q naught, we're going to start at the set containing Q naught. And we'll tweak that one here in a second. But hopefully so far it's just appealing to your intuition. Rather than starting at Q naught, we're going to start at the set containing Q naught.
So it's still Q naught?
Almost. Remember now, what are our states for our machine over here? They're sets of states of our initial machine. If our start state here was 1, then our start state here is a set containing 1. Almost. It's not really. It turns out it's a set containing 1, 3, but that's because we have this epsilon transition. And we'll come back to that. If we didn't have this epsilon transition, then our start state over here would have been just a set containing 1.
Oh, I see.
You with me? So we'll deal with the epsilon transitions. We're going to ignore them for the first part of our proof and then show how we bring those in.
Sorry, I have a question when you say that Q prime is equal to the
Power set of Q.
Is a state an undefined term in this course? I'm just
A
confused when you
state,
define it
you
as a
can
state.
use any label to signify a state. I can signify it with numbers, I can signify it with letters.
Right, but here you're saying that a state
I'm
is a set.
using states, I'm using sets of states of this machine to signify states over here.
So,
And there's nothing invalid about that. I don't have to do that. It's just a convenient way so that you can see how I was thinking about this machine.
So you're treating all those characters.
It's always just a label.
A single symbol.
Yes,
essentially.
we're essentially treating that, not a symbol, because remember, a symbol is a technical term for us. A symbol is a member of our alphabet, but it's just the label of that state. And I can use any symbols I want to label that state.
So you're not defining a state.
I'm telling you how we're going to label the states on this machine. If the states on this machine were labeled Q naught, Q1, Q2, then the states on this machine are going to be sets of Q naughts, Q1s, and Q2s.
Okay.
So if our symbols, or if our states over here were capital Q, then our sets of states over here, then our states over here are going to be the power set of capital Q.
They're labeled like the power set of capital Q?
Yeah, because we're going to need exactly that many states.
But they're
Because
not
what is this
necessarily-
thing doing? It's keeping track of all the possible states this thing could have been in. So it helps us reason about it to label it that way.
Right, so they're labeled like the power set of Q, but they're not necessarily, like they aren't exactly the power set of Q?
I don't know that there's a difference there.
Well, it's just weird to me that you're defining a state as a set. 'Cause-
Everything sets,
Okay, fair enough.
right? And so it's just a matter of the location of that thing that we're saying, because everything is just sets of sets of sets of sets of sets. That's what everything is. And we're saying this set of sets of sets of sets of sets of sets, I'm going to call the first one states.
Alright,
That's thinking about on a really low level.
that makes more sense.
Alright, back to high level thinking. This is 1, 2, 3. This is going to be the power set of 1, 2, 3. Right? So, Q prime is the power set of Q. Our new start state is going to be the set containing our start state. Our new accept states are going to be any how can I say this? Remember, Q prime is all possible subsets of Q. So our new accept states is going to be any subset of Q that had an accept state in it.
What does the R mean?
R is a member of Q prime. Q prime is one of these. So R could be the set containing 2, 3. So R is in 2, 3. So R right now we think about as 2, 3. So we take all the R, which is going to be each one of these things. R is iterating over all these. In Q prime is a set of all these states here, such that R intersected with F is not empty. What is F? F is the set containing 1. When I take the set containing 2, 3, and I intersect it with the set containing 1, what do I get?
1, 2, 3.
When I intersect it.
Nothing.
Nothing.
Empty set.
What's everything that's in the set containing 1 and in the set containing 2, 3?
Empty set.
The empty set. So that was equal to the empty set. If R was equal to the set containing 2, 3, and F was equal to the set containing 1, their intersection is nothing.
Yeah.
So our accept states for our new machine are going to be all those subsets that don't have an empty intersection with our initial accept states. So for this example, F here is a set containing 1. R, we're iterating over all of those. So let's just do this one explicitly. Let's say that R is the empty set. What's the empty set intersected with the set containing 1?
Empty set.
The empty set. So is it not the empty set?
No.
No. So this is not an accept state. Let's look at this one, the set containing 1. So if R is the set containing 1, what's the set containing 1 intersected with the set containing 1? It's not the accept state, or it's not the empty set. So we do accept. So that is in F prime.
Oh, I see.
F prime is a set of all subsets whose intersection with our initial F, the set containing 1, are not empty. They have something in common with F.
Interesting.
Yeah.
Try one more. So R could also be the set containing 1, 2. So if R is the set containing 1, 2, the set containing 1, 2 intersected with the set containing 1 is not the empty state because it has a 1. So this is an accept state. So F prime in our case was the set containing 1, the set containing 1, 2, the set containing 1, and the set containing 1, 3, and the set containing 1, 2, 3. It was all the sets, it was all the things in Q prime up here. Here's Q prime. It was all the things in there, such that when you intersect it with this set, you didn't end up with an empty set. When I intersect that with that, it's not empty, so it's in F prime. When I intersect that with that, it's not empty, so it's in F prime. When I intersect that with that, it's not empty, so it's in F prime. Notice that the set containing 2 intersected with the set containing 1, that is empty. So the set containing 2 is not listed down here.
Yep.
Think we got it? Over-explaining? All right, now we get to the hard part. Transition function is always the hard part. And for any subset of Q, or for all R and Q prime, for any subset of Q, and for any input symbol, we define delta prime on R with that input symbol to be the union of all the sets we could have reached for each little r in big R. Now I think that was a mouthful, so let's write this one out explicitly, just to make sure we get it. So delta prime is going to take as an input an R, which is a subset of Q. Give me some subset of Q for our example. 1, 3. And it takes some input symbol. Give me some input symbol. B. And it is going to be equal to, in our case, this is the union of all little r in big R. Big R in our case is 1, 3. Of delta Notice that's delta, not delta prime, so using our already defined transition function. For little r, and that same input symbol, b.
So what is that union thing?
I know. So what is this saying? This is saying plug in 1 for little r, plug in 3 for little r, and union up the set you get. So this is saying do delta of plug in 1 for little r and b, and union that with delta of 3 with b. And if we would have also had 2 in there, then I'd also union delta 2 of b. And let's keep going. What is delta 1b? Look over here, delta is already defined. 1b is a set containing 2. And we're going to union that with 3b. 3b is the empty set. So in this case, it came out to a set containing 2. On 1, 3, when you read a b, you go to a set containing 2. That's what we were doing. To capture just what we were thinking when we did that precisely in math, here's how you got to write it out.
Do they have software that like you could plug in a definition, a lot like indentation, and then compare it up with your model, and it would tell you whether or not it properly defines it?
I'm not sure what you mean. I mean, because every time you're plugging in with software, you're perfectly defining things. You're giving them definitions. That's what you do over and over again. Every time you define a function, you define it to be that body. Every time you define a variable, you define it to be that value. Okay. Do you want to see another explicit one, or do you think you got it? Here, well, let's keep that written up and then reread it over here, and maybe that will do it for you. Okay, so our new transition function, delta prime, this is a delta prime, that's the little erase right there. Delta prime on some subset of Q and some input symbol is equal to the union of all the possible states you could have reached reading that input symbol from all the states in big R. For each little r in big R, see the states you could have reached reading that input symbol, union them all together. That's where we go to on prime.
Yep.
Remember to look over here. R in our case was 1, 3, and A in our case was B, is equal to little r in big R, delta little rb. Same thing we have written right here. That is right there, and then I just showed you exactly what this means. This means replace your r with 1 and replace your r with 3 and union up the results. When you replace r with 1, you got that. When you replace r with 3, you got that. Union up the results. That we value to that we value to that. Union them together. Away we go. Think you got it? Want to see another concrete example of it? Just so you look at it.
I got a concept, I just don't think I'm going to remember it.
That will often be the case. You can understand it when you see me writing it here on the board. Then later you get confused, and that's the beauty of homework problems. They force you to go back and use the material. And then you're like, oh wait, what did that mean again? And you have to go look at the definitions. And then you struggle again because now you don't remember because I'm not here reminding you. And then you get to click again there on your own. And then when you get that, then you've really not learned it yet because you'll probably have to do it like 5 more times. And yeah, there's no shortcut to just getting this stuff. It's dense. The only way to get it is keep working with it. So, I don't know. Think you got it? For the proof at least? Okay, so that's our new transition function. Now, thus far, we have ignored all epsilon transitions. This proof is going to get a little bit messier.
Oh.
And so we need to modify our start state and the transition function accordingly. We need to take into account epsilon transitions. So I'm going to define a new function that's going to help us do this. So complete the new function, nothing we did before any of this. I'm going to define a completely new function. I'm going to call it the E function.
Is there any reason for that?
Yeah, because it makes empty transitions. So the E function, sorry, bad notation. I'm defining an E function. It's going to be a mapping from some subset of Q to some other subset of Q. So you're going to give it like the set containing 1 as an input symbol, and it's going to spit out like the set containing 1, 2, 3.
That could be itself. That makes sense.
Right, and it could be itself. So it's defined from this set to this set.
So prime is supposed to be curved like a quotation mark?
Yeah, just like an apostrophe.
Oh yeah, that one, yeah.
Yeah, that's what those are supposed to be. Sorry.
Okay.
Good point. Apostrophes. Anyways, so our empty transition function goes from some subset of states to some subset of states by what? And I didn't want to write this one out explicitly because it becomes a nightmare. So I'm going to rely on your intuition a little bit here. Our empty transition on some set of states R goes to the set of all the states in Q where Q can be reached from a state in R by an empty transition. And end set here.
What's the difference between little q and r?
So let's write this one out explicitly. There's only one case where it really makes sense up here. So E of the set containing 1 is equal to the set containing 3. E on some set of subsets, like 1,
Yeah.
is equal to, sorry, we're past it, is equal to the set of all the things in Q, set of all the states up here, that could have been reached from a state in R by an epsilon transition. So what are all the states in R? Just 1. What are all the states that could have been reached from 1 on an epsilon transition? Just 3. And similarly, notice that E of 1, 3 is equal to what are all the states that can be reached from either 1 or 3 on an empty transition?
B. Then A. Or,
Oh, sorry, I'm looking wrong.
are you looking for 3?
Without reading, maybe I shouldn't have said reading states in R. I shouldn't have said an epsilon transition. I said without reading a symbol. Let's say that. In R, without reading a symbol. Or in other words, reading an epsilon symbol is an option. Without reading an input symbol. Okay, that's what I really want. So I don't want you to be confused by one.
Are we in N or M right now?
Over here, we're looking at this machine. We're talking about how to construct this thing. So we're looking at this thing, right?
Yeah.
What are all the states I can reach from state 1 or 3 without reading anything?
Yeah, 3. Is that what you're looking for?
Still just 1 and 3. And so I lied up here when I wrote just 3 because it's 1 and 3. Not that we have to make an epsilon transition, but that without reading anything. That's the difference.
Okay. Oh.
You see what I mean?
Yeah, nothing changes.
So we can stay in state 1 or we can go to state 3. And most of the times, E of whatever state just spits out that same thing. So if we did E of just a set containing 2, then that's just going to be equal to the set containing 2. And it doesn't change anything. So it only adds to it if there was a possible epsilon transition.
Okay, yeah.
That's what E is supposed to be. So it lets you do the epsilon transitions if you want, is what E does. You don't have to take them, but you can take them. That's what E allows you to do. You with me?
So E always relates to epsilon.
It lets you take the epsilon transitions if you want, or stay. So from 1, we could get to 1 or 3 by reading nothing. You with me? Okay, so now with that definition for E, let's now go back and define our start state the exact way we want. So our start state, our new start state for this machine over here, is going to be equal to the E transition on the set containing our start state over here. So our start state over here, Q naught prime, is going to be equal to our E transition on our start state over here, 1. And what is E on the set containing 1? 1, 3. Which then is our start state over here, which is exactly what we said.
Yeah.
And now our transition function, rather than transitioning to the union of all the states that could have been reached, it's going to be the union of all the states that could be reached, and then the states that they could have also reached by an epsilon transition. So remember, this right here already gives me all the states that could have been reached by reading the symbol A, right?
Oh, you're not talking about finished states anymore.
This is our transition function.
Yeah, okay.
So all the states that we can reach from R on some input symbol A. It was the union of all the states that we could have reached for each of those R's on the input symbol A, right? Together with any epsilon transitions that they could have done. So let's write that one out explicitly for an example where that comes into play. And then hopefully this makes the definition completely clear. Then maybe we'll end it after this definition. Okay. So now we're saying that delta prime on the input, in this case I want just, let's see, we'll do just 3 on an A. You with me? So we're starting out in this state and we're going to read A.
Okay.
So this is equal to our E function on the union for all little r in big R. Big R is just a set containing 3 this time, right?
Yeah.
Of our previous transition function on that little r and our input symbol A.
Why are you ever going to need that little r, big R, if there's only one?
You don't need it when there's only one. I'm just writing it so it perfectly matches what we have written over there.
But there's if it's always an NF, never mind, keep going.
It could have been more than one. It's, in this special case, it happened to be one. In fact, good point. Let's say that we were in 2-3 and we read an A. I like your thinking. Let's do that. This will still work. So delta prime, we're in 2-3, and we're reading an A. This is equal to the empty transition on the union for all little r in the set containing 2-3 of our regular delta function that we already had defined on little r in the input symbol A, right? Which is equal to our E transition on, let's expand that out. That says we do delta on 2 with A, union together with delta on 3 with A. Right? Writing that out for each little r is written out right there. This is equal to our empty transition on. What is delta on 2 with A? Delta on 2 with A is 2-3, set contain 2-3. right?
2, 3, and 1, 3.
2, 3. And then 3 on an A. Oh, because we were already doing the epsilon transition for us. Son of a gun. Because the way we defined our delta over there was not already making those. So, it,
Now it's just 1.
don't ignore the table. 3,
It would just be 1 inside and then epsilon to make it 1, 3 outside.
yeah, so 2 on an A gets there. 3 on an A, we'll say just goes to 1. Let's see if I broke it just barely. Oh no. Yeah, I was overthinking it on this.
That's what I was saying before. That table makes a lot more sense than it.
Way overthinking on this. On this, we should literally just write out exactly what the transitions are here. Let me make sure we did this right. 1, where do we go on an A? Nowhere. Where do we go on a B? To 2. Where do we go on epsilon?
3.
To 3. Okay, yeah, because we actually have that arrow in it. So this better be the only epsilon that we have today. Sorry, yeah, I wrote the table wrong. No wonder we're getting confused. All right, 2 on an A, where do you go? You go to 2 or to 3. Okay, that's right. On a B, where do you go? Just to 3. And on an epsilon, you don't have any epsilon arrows. You on an A go to 1.
I see where.
Okay,
Yeah.
yes, so we did mess up before. Okay, perfect. Good. Glad that our example caught our mess up. So, now, delta 3 on an A, where do we go?
1.
3 on an A, we go to 1.
Yes.
Oh crap, but 2 on an A, we already get 3 on there. So we're not going to see how the empty helps.
Yeah, that's confused me too.
Ah! Sorry, we can't have multiple states for this one. I may have to do just
Which
3.
one's like 1, 3? Or 1, 2?
Maybe we can do 1, 3. Okay, we'll do 1, 3. So if we do 1, 3 on an A, okay, yeah, we should be fine. Okay, 1, 3, A, so replace that with a 1. Okay, yeah, this will work. There we go. This is equal to our empty transition on delta when we plug in a 1 and an A, union with delta when we plug in a 3 and an A. Okay, this is equal to our empty transition on, what's delta 1A?
Empty set.
1A empty set. Union with delta 3A,
Set containing 1.
the set containing 1. Which then gives us our epsilon transition on the empty set union with the set containing 1 is just a set containing 1.
Yep.
Which now is equal to, what are all the places we can reach from the state 1 without reading a symbol?
3.
1 and 3.
1 and 3.
We can stay at 1 or we can go to 3 without reading anything. So this is a set 1, 3.
Without reading anything or with reading
With-
epsilon?
Without reading anything includes reading epsilon. When you read epsilon, you didn't read anything.
Yeah, that's why. I
Epsilon is the empty string. Okay, so there we go. And that's what we wanted. We wanted 1, 3 when you read an A to go to 1, 3. So 1, 3 on an A, you go back to 1, 3.
If you're
Remember, delta prime is our transition function we have over here. And that's what we wrote.
So if it was epsilon with a set of 3, it would just be 3. Is that correct?
You're saying if we did this, you're saying E on the set containing just 3?
That would just be 3.
That is just equal to the set containing 3, yes. So this E function only changes the set if there were epsilon transitions. And it can only make the set bigger, it can't ever make it smaller.
So everything we really do in defining is just define the patterns. That's all it seems like we're doing.
Well, we're creating rigorous definitions. It's almost like if I were trying to tell a computer how to do this process,
Right.
then we need strict rules that we use. Okay, there we go. And that's our new transition function. Okay, so there we go. There's our new transition function. And that's how we build the machine M, recognizing the same language. So if you follow this procedure for any NFA, you'll always be left with a DFA that recognizes an equivalent language. Good? Okay, let's just say this corollary since it's straightforward and just follows from this, and then we'll be done. So what's our corollary here? Our corollary is A, that's the set, A is a regular language if and only if an NFA recognizes it. A language is regular if and only if it can be recognized by an NFA. The language A is regular if and only if an NFA recognizes it.
What's the difference between a corollary and
So a theorem, the corollary is just a theorem. And a lemma is just a theorem. Corollary, we specifically call it a corollary, meaning this we almost get for free from the thing we just proved.
Oh.
That's typically what it means. Lemma means this is something that we're proving, not because we really care about it, but because it's going to help us with the proof that we care about. But really, they're all just theorems. It's just to help give you a little bit more context. So corollary from this theorem. A language is regular if and only if an NFA recognizes it. So let's do it this way first. Assume A is a regular language. What does it mean for a language to be regular?
A DFA recognizes it.
That means some DFA recognizes it. That's what it means for a language to be regular. You can build a finite state machine that recognizes it.
Okay.
And so some DFA recognizes it. Now we already know that every DFA is an NFA. So some NFA recognizes it, since DFAs are NFAs. A DFA is an NFA. So the first way is done. We just really show that if a language is regular, then an NFA recognizes it. Now we need to show the other way. If a language is recognized by an NFA, then it's regular. So let A be the language recognized by some NFA N, where N is an NFA. Well, then by this theorem up here, there must exist some machine M such that M is a DFA and the language of M is also A. And since the language of M is equal to A, then A must be a regular language because it's recognized by some DFA. Follow the logic there? Cool. So we'll end it there, give you a little bit of a heads up from where we're going next. So far we've talked about the languages recognized by DFAs. Now we've also talked about the languages recognized by NFAs. Next we're going to talk about the languages recognized by regular expressions. We'll do more with NFAs next week. Then we'll finish and we'll move on to regular expressions. And then we'll talk about what we call regular grammars. And we're going to show that all these are logically equivalent to each other. They're all logically equivalent ways of talking about the exact same thing. And we call all the languages recognized by those things regular languages. And that was the first set in our little bullseye that we set up. As at first we talked about these problems that we can solve, those were the regular languages. Then we talked about those ones, the ones done by context-free grammars, then the ones that can be done by computers in general. So when we're done with that, we'll have finished talking about this category right here. That's big picture where we're going. And so we've shown that arrow.
So you're saying that this is kind of just the found, is not necessarily useful in itself, but somehow useful when you build on top of it?
It's useful in itself in that, useful is such a relative term. Useful for what? It's often useful for programmers simply for working with the abstractions. Oftentimes when you're programming, your job is to design an abstraction to solve some complex problem. And your job is to think of as elegant and reusable an abstraction as you can to solve that problem. And that's exactly what all of math is. It's coming up with abstractions to design, to solve these types of problems. So that's one of the big uses there. Another big use is you can't begin to start building a compiler without knowing a bunch of this stuff. You want to build a compiler, you need to know some basics about state machines. Every compiler is we'll eventually talk about them, but a context-free grammar. So,
Cool. Look forward to that.
anyways, yeah. So, useful for some things. Anyways, that's all we got. We'll end it there. Had a lot more today, but